Okay, Calculus 3 students. Hey there, this is Mr. Lewitt. This is a tutorial video that I'm going to do for part 2 of the chapter 12 homework. So, my goal is to cover 10 problems in this video, unless the video becomes extremely long, and in which case I'll have to break up the 10 problems into 2 videos, but I'll do my best to get it all done in one video. Hold on, before we start, okay, let me just make sure I have my drawing tool ready. Okay, so my goal, let me see. My goal for this video is to do the following problems. Oh, 1 second. So my goal for this video is to do problems 1, 46, 53, 54, 55, let's see, 56, 112, 119, and finally 120. Excuse me. So let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. I thought that was 10 problems. Let me see, am I missing something? Oh, yes, I am missing something. Problem number 49. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the 10 problems I would like to do in this video, and these problems are taken from part 2 of the chapter 12. Oops. I can write that a little bit better. Chapter 12 homework. Okay. These 10 problems are taken from part 2 of the chapter 12 homework. Okay, and of course you should remember that my problems are going to look just a little bit different from your problems. They're going to be similar, but the numbers could be a little bit different. Okay? By now you should know that. If you've been working with Pearson since the beginning of the semester, you should know that. Okay, so why don't we get started? Okay, problem number 1. Suppose you are standing on the surface. Z is equal to f of x and y at the point A, B, f of AB. So x is equal to A, y is equal to B, z is equal to f of A and B. Interpret the meaning of the partial derivative of f with respect to x at AB and the partial derivative of f with respect to y of AB in terms of slopes or rates of change. Let me see here, the slope of the surface in the direction. Okay, so it should be A The partial derivative of f with respect to x at AB is the slope of the surface in the direction parallel to the x-axis, and the partial derivative of f with respect to y at AB is the slope of the surface in the direction parallel to the y-axis, both taken at the point AB. It should be correct. Okay, so let me just make this comment here, and it would help if I could draw something for you. Okay, so we have x and we have y. This is x. This is y. And we have some point here, and that is AB. Now, what's important to remember is this. When you are looking at the partial derivative of f with respect to x, you are looking at the slope in this direction, or maybe, this direction. When you're looking at the partial derivative of f with respect to y, you're looking at the slope in, let's say, this direction, the direction of y. Okay, actually, when you're looking at the direction of x, generally you're considering the slope in the direction of the positive half of the x-axis, right over here, okay? However, you have to remember that in the Calculus 3 course, there are many other directions. There's this direction, there's this direction, there's this direction, we have this direction, we have this direction, yes? We have this direction, we have this direction. Okay, you get the idea. And that's when we start talking about directional derivatives. Directional derivatives those are fun problems to do, and they're pretty easy. And we're going to see them at the end of the video. And when you're doing those problems, you get to play around with the dot product, which we explored in the previous chapter, the last chapter. Okay. Let's move on to problem number 46. Let's move on to problem number 46. Okay, that's my dog, and we're just going to ignore him because, that's what we're going to do. We're just going to ignore him. Okay, so for number 46, use the definition of differentiability to prove that the following function is differentiable at 0, 0, the origin. You must produce functions epsilon 1 and epsilon 2 with the required properties. This problem is kind of nice because they walk you through the proof. Okay, they walk you through the proof step by step, which is kind of cool. What is the first step in proving differentiability? The first step is to show that the partial derivatives actually do exist. That's going to be the first step. Well, this is easy. The partial derivative with respect to x, that's simply going to be 1. And the partial derivative with respect to y is also going to be 1. What is the next step? The next step is to show that, let me see here, the change in z, or delta z, is going to be equal to f of 0 plus delta x, 0 plus delta y, minus f of AB is equal to the partial derivative of f with respect to x at the point 0, 0 times delta x, plus the same, the partial derivative with respect to y of 0, 0 times delta y, plus epsilon 1 times delta x plus epsilon 2. Well, now wait one moment. Okay, so you know what? It's going to be C. These answers look very similar, but they're not the same. So let's take a look. Hold on one second. I'm looking at, okay, it should be C. Show that the change in Z or delta Z is equal, oh, wait a minute. No. It should not be C. It should be D. Sorry about that. Let me check to make sure. I'm pretty sure it's, let me read this more carefully. The change in Z is equal to f of 0 plus delta x, 0 plus delta y minus f of AB is equal to partial f with respect to x of 0, 0. D doesn't make sense. Hold on one second. Okay, these answers here, hold on one second. These answers are not very compelling. You know what, it's going to be, hold on. Their answers are so close, you really have to read them very, very carefully. The change in Z, or delta Z, is equal to f of 0 plus delta x, 0 plus delta y, minus f of AB, which is like the definition of the derivative from calculus 1, is equal to partial f with respect to x at the point 0, 0 delta x, plus partial f with respect to y of 0, 0 delta y, plus epsilon 1 times delta x plus epsilon 2 times delta y, where epsilon 1 and epsilon 2 are functions that depend only on delta x and delta y. And as they approach 0, delta x and delta y also approach 0. It should be A. Okay, yeah, this one's tricky because all of their answers look similar, but they're not exactly the same. They're not exactly the same. Evaluate the middle expression from the equation in the previous step. So the middle equation is simply going to be 1 times delta x plus 1 times delta y. So you have delta x plus delta y. And of course, they're multiplied by 1 because those are the values of the derivatives, the partial derivatives, right? So that should be correct. Find the rightmost expression found for delta z. Choose the correct answer below. They kind of give you that answer right over here. So that's going to be delta x plus delta y plus epsilon 1 delta x plus epsilon 2 delta y is equal to delta z. And that should be correct. Okay, this is the tricky part. I think this is the last part of the problem, and this part is a little confusing. So hold on one second. Let me, I need a blackboard kind of, well, this is really terminal. It's not actually a blackboard, but we're going to pretend that it's a blackboard. Okay, so in the last step, what they're asking you to prove, what are the, okay, so they're asking you to prove this. Delta x plus delta y is equal to epsilon 1 well, they're actually, hold on one second. They're, okay, let me start over. Okay, so, okay. what they're asking you to show is that delta x plus delta y is equal to the change in x, or delta means change, plus delta y plus epsilon 1 delta x. Okay, I'm writing this with my trackpad, so it's really not that easy to do. Hold on one second. Let me expand this just a little bit. Plus epsilon 2 delta y. Okay. That's really what they're asking you to do in the last step. Now, this is just basic algebra, but it gets a little bit confusing. So obviously, this is going to be true if epsilon 1 and epsilon 2 are both equal to 0. Okay, so let's see. If epsilon 1 and epsilon 2 are equal to 0, then we know that the equation is going to have to be true. That makes sense because then these terms just cancel out completely, okay? But what if epsilon 1 is equal to what if epsilon 1 is equal to negative delta y? And what if epsilon 2 is equal to delta x? So if epsilon 1 is equal to delta y and epsilon 2 is equal to negative x, these two terms will also cancel out to 0. Okay, and then what if here, hold on one second. What if we have the opposite situation where epsilon 1 is equal to negative delta y and epsilon 2 is equal to delta x? Again, these terms will cancel out to 0, and you have delta x plus delta y is equal to itself, which is delta x plus delta y. And that should be correct. Okay. So, if you just think in terms of algebra, this problem is doable. I realize it's a little bit tricky, but they kind of coach you through the steps of the proof, and you just have to follow the steps. You just really have to follow the steps. And also remember, guys, I'm giving you 10 attempts on each problem. That's a lot, okay? If you get the problem wrong the first time, you have 9 more attempts to get the answer correct. So really, everyone should end up with like a 98, 99, or 100% on the assignment. Okay, so that wasn't too bad. Let me erase this. And one second. Oops, sorry about that. Okay, let me close this. Okay, let's move on to problem number 53. Okay. If w is a function of x, y, and z, which are all functions of t, explain how to find dw dt. If w is a function of x, y, and z, okay, if w is a function of x, y, and z, which are all functions of t, explain how to find dw dt. So this is the chain rule, which you should read about in your book. Okay, so I believe the answer is simply going to be B. We have partial w with respect to x. times dx dt plus partial w with respect to y times dy dt plus partial w with respect to z times dz dt. And that's going to be your answer. And that's really the definition of the chain rule. That's number 53. This is correct for using the chain rule for differentiating with three intermediate variables x, y, and z, where x, y, and z are all functions of t. Okay, let's go on to 54. If z is equal to f of x and y, and x is equal to g of s and t, and y is equal to h of s and t, explain how to find the partial derivative of z with respect to t. Okay, so 1 second. For this one, I may draw a tree diagram. Let me move this over. I think for this problem, we're going to draw a tree diagram, which should help. Let's see. Okay, so z is a function of x and y. Z is a function of x and y. And x is a function of s and t. X is a function of s and t. And we know that y is a function, y is also a function of s and t. Okay, and z is equal to f of x comma y. Okay, and then we have x is equal to g of s and t. And then we have y is equal to h of s and t. Okay, so that's my tree diagram. And then it asks me to find the partial derivative of z with respect to t. So in order to do, hold on 1 second. In order to do that, I basically have to consider the branches of my tree. What I'm really looking for is this branch. The partial, let me change colors here if that will help you. Yeah, that should work out okay. So I'm looking for the derivative, the partial derivative of z with respect to t. But I can't forget that x also depends on s. Okay, so I'm looking for the partial derivative. I'm looking for the partial derivative of z with respect to t. Okay, but I have to remember that x, well actually, 1 moment. The partial derivative of z with respect to t, okay, so I have to remember that x is a function of s, well, x is equal to g of s and t. X depends upon s and t. So I'm looking for the relationship between z and t, the partial derivative of z with respect to t, or partial z with respect to t. But consider this branch right over here. Consider this branch as well. Okay, so what I'm going to have to do actually In order to figure out the partial derivative of z with respect to t, I have to take the partial derivative of z with respect to x times dx dt, and then add it to the partial derivative of z with respect to y multiplied by dy dt. And you can see that if you look at the branches of my tree, at the branches of the tree diagram. So I have the partial derivative of z with respect to x multiplied by dx dt, and I have to add that to this other path, the other path that leads from z to t. There are two paths that lead from z to t, zxt and zyt. So it's partial z with respect to partial x times dx dt plus partial z with respect to y times dy dt. So you're actually adding these paths. So let me see here. The answer should be, I believe it's going to be choice A. So partial z with respect to partial t is equal to partial z with respect to x. Oh, no, it's not. Because dx dt, that's not a partial derivative, it's an ordinary derivative. So, oh yeah, but x is a function of two variables, so that is a partial derivative, right? So you know what, it should be A. Actually, yeah, so my notation is a little sloppy. This should actually be, these are partial derivatives, not ordinary derivatives. These are partial derivatives because x and y are functions of more than one variable. So my notation got a little bit sloppy. So I believe it should be choice A. Okay, one moment. Choice A. And that is correct. So this is the correct method of multiplying each of the partial derivatives of f by the t derivative of the corresponding function. Okay, so that was number 54. Let's move on to number 55. Okay, 1 second. Okay, let me erase the tree. But basically, as long as you do a tree diagram for these chain rule problems, you really should be okay. You just have to be careful to follow the branches of your tree, and you should be okay. I like to do the tree diagrams. I think they're very helpful. They should help you visualize the problem a little bit better. 1 second. Okay. Number 55, which I believe is also a chain rule type of problem. If f of x and y is equal to 0 and y is a differentiable function of x, explain how to find the ordinary derivative of y with respect to x. Okay, so this is simply going to be, I believe it's A, use the chain rule when taking the derivative of the left side of the equation. Well, actually, it should be both sides. Use the chain rule when taking the derivative of both sides of the equation with respect to x, and then solve for dy dx. So I believe it should be C. It should be option C. And yeah, of course, you can't, if the partial derivative of f with respect to y cannot be 0, because then you're dividing by 0. So long story short, I spent a lot of time on the last problem, so on this problem I'm not going to spend a lot of time. But let me just say this. Something that you should really memorize, because it could show up in other classes. let me see. Let me turn on my drawing tool. Um, if you have a function of f of x and y, so f depends on x and y, and you're looking to find the ordinary derivative dy dx, just remember, and this is something that's worth memorizing, this is going to be negative f with partial f with respect to x, negative partial f with respect to x, divided by partial f with respect to y. Okay, and actually this is something you could even prove using Mathematica. I don't want to explain that right now because then, the video is going to become even longer, but this is something that you should really commit to memory. This is something you should really commit to memory. So if you have a function f of x and y is assumed to depend on x, then the ordinary derivative dy dx is equal to the negative partial f with respect to x divided by partial f with respect to y. Okay? So this is something you should commit to memory because it does appear in a lot of other subjects like physical. I'm thinking specifically of physical chemistry and also physics. Physical chemistry and physics. So this is something you should really memorize for those courses because it will show up in those courses, okay? But this is important. You really should remember this. Okay. Okay. Next, so that was problem 55. Let's move on to problem 56. Use the chain rule to find the ordinary derivative of z with respect to t, where z is equal to 2x sine y, and x is equal to t cubed, and y is equal to 3t squared. Now, for this one, guys, it's tempting to use Mathematica, but let's not use Mathematica for this problem. Because we're going to use Mathematica for the other problems anyway. But for this problem, let's try to do it the old-fashioned way so that we don't get too lazy. Personally, I love Mathematica. I think it's a wonderful tool. But if you use it inappropriately or if you use it too much for certain problems, you can get very lazy. Okay, you can get very lazy. So let's do this the old-fashioned way. Let's see. What did I just do? Oops. Okay. Hold on. Let's start that again. Okay. Oh, wait a minute. What? Okay. Hold on one second. We're having technical difficulties here. Sorry about that. Okay. Oops. Okay, so we have we're looking for the ordinary derivative dz dt, and we know that z is equal to 2x sine y, and we know that x is equal to t cubed, and we know that y is equal to 3t squared. And we're looking for the ordinary derivative dz dt. So this is actually going to be partial z partial x times dx dt plus partial z partial y dy dt. Okay, so then what is partial z with respect to x? Partial z with respect to x is going to be 2 sine y. And then partial z with respect to y, that's going to be 2x cosine y. And then dx dt is equal to 3t squared. And then dy dt is equal to 6t. Okay? So here, now you got to be careful. So I could write 2 sine y times 3t squared plus 2x cosine y times 6t. 6t. Well, there are a couple problems here. Oh, I see. They're just, okay, I'm giving them the complete answer. They just want the, okay, sorry. So they're looking for the intermediate answer. So 2 times sine y, and that should be correct. Okay. And then this is simply going to be 3t squared, and that should be correct. Partial z with respect to y is simply 2x cosine y, and that should be correct. Dy dt is simply equal to 6t, and that should be correct. And then finally, we have to put the whole thing together. So putting it together is the hard part. So I have to remember, I could write this, okay, sine y, times 3t squared. That looks awful. First of all, 2 times 3 is 6. So just put 6, okay. Also, we should put the t squared in front. Oh, hold on, I just got rid of my 6. Okay. And then What is y equal to? Y is equal to 3t squared. Nice. Okay. Plus, now I could write this 2x cosine y times 6t, but again, that doesn't make any sense. So 2 times 6t is 12t. X is equal to t cubed. T times t cubed is t to the 4th power. Ugh. And then y is equal to 3t squared. Okay, so just doing a little bit of simplification there, a little bit of algebra, and that should be correct. Okay, so that's not too terrible, right? Next question. We have 3 more problems, 112, 119, and 120. So for those problems, we're definitely going to use a whole lot of Mathematica, okay? So let me just erase all the scribble. And 1 second. So problem 112. Okay, consider the paraboloid f of x and y is equal to 18 minus x squared over 4 minus y squared over 25. And this particular point, x is equal to 2 square root 2 and y is equal to negative 10. On the level curve, f of x and y is equal to 12. Compute the slope of the line tangent to the level curve at P and verify that the tangent line is orthogonal to the gradient at that point. Okay. So first of all, we should draw this. Okay. So we have f of x and y is equal to 18 minus x squared over 4 minus y squared over 25. Okay. And we have f of x and y is equal to the level curve for this problem is f of x and y is equal to 12. Oh, I don't know. This is going to be like an oval or a circle. So let's say x goes from negative 30 to positive 30 and y goes from negative 30 to positive 30. Okay. The range is a little too big. We could make that a lot smaller. So let's say x goes from negative 15 to 15 and y goes from negative 20 to 20. Here, you know what? I'm going to turn off the background color because that might be getting in the way a little bit. There we go. Well, that's not bad. We could 15 to 15. Okay, that's not too dreadful. And We could make that look a little bit better. Frame tick style, directive, font weight is bold, font color is black, font size is let's say 20, and font family is, I like Arial. Image size, let's make this much bigger, 500 pixels, and then contour style, absolute thickness 5, black. Okay, that's much nicer. That looks much nicer. Frame, well, let's see, grid lines, automatic. Okay, that's not too bad. Okay, so this is the projection of this function onto the plane z is equal to 12. Z is equal to 12, or f of x and y is equal to 12. Okay, this is the projection of the function onto the plane z is equal to 12. Now the point is 2 square root of 2 and negative 10. 2 square root of 2 and negative 10. So let's draw that. Let's see. We're going to draw that. List plot 2 square root of 2, negative 10. Plot markers. Filled circle. Let's say 30 pixels across, and plot style can be opacity red. We're going to make it a little transparent. And if I'm combining two pictures, I need to use the show command. I could even make that a little bigger. How about 35 pixels? Okay, so here's the point. I can tell just by looking at the picture that the slope is going to have to be positive. The slope is going to have to be positive. The slope of the tangent line is going to have to be positive. So how do I find the slope of the tangent line? That's going to be very easy. Now I'm going to be lazy for this problem. I'm going to let Mathematica do some of the work for me. Okay, derivative f of x and y with respect to x, negative, control divide by, derivative of f of x and y with respect to y, negative 25x over 4y. X is equal to 2 square root of 2. And we're going to replace y with negative 10. So the answer is going to be 5. Hold on one second. 5 square root of 2 divided by 5 square root of 2 divided by 2 square root 2 times square root 2, which is 4. Divided, one second. Divided by 4. And it should be correct. Okay. How do you know the gradient and tangent line are orthogonal? Okay, so that's going to be very easy. The slope of the tangent line M can be used to write a vector in the direction of the tangent line. The dot product of this vector and the gradient is 0, so they are orthogonal. Okay, so for this problem, guys, all we have to do, what they're talking about is this. Well, they're kind of making it a little more complicated than necessary, but basically the gradient vector that they are talking about is equal to derivative of f of xy with respect to x, and then derivative of f of xy with respect to y. Oh, and then of course, almost forgot, x, it has to be replaced with 2 square root of 2, and then y has to be replaced with negative 10. Okay, so what they're talking about is, yeah, that's going to be the gradient vector. Oh, actually, no, wait a minute. It's going to be A. Sorry about that. That's going to be A. And the gradient vector is negative square root of 2. Hold on one second. Negative square root of 2 and then 4 over 5. 4 over 5. And that should be correct. Now, what they're talking about, the tangent vector is going to look like this. And the slope was 5 divided by 2 square root of 2. So if I have the dot product of the tangent vector and the gradient vector, the answer is 0. If I want to actually find the tangent line, okay, that's going to be pretty easy to do because I have to remember that y is equal to the slope times x plus intercept, or intercept is equal to y minus slope times x. Okay, so the intercept is equal to y, which is negative 10, times the slope, which is this value right here. This is my slope. Let me just copy that. Oh, one second. This should be minus. Okay, negative 10 is the y value minus the slope times the x value, which is square root of 2. Oh, sorry about that. Actually, these are going to cancel out. So you're going to end up with negative 15. The answer is negative 15. So what I could do, go up here, copy this, put it down over here, and let's say that I want to graph the tangent line, plot, and my slope is equal to 5 divided by 2 times the square root of 2. So this will be slope times x plus intercept, where x is going to go from negative 15 to 15. And let's say this will be thick, blue, and dashed. Okay, and that's the slope of my tangent line. And of course we can see, it must have a positive slope. Okay, so that's pretty simple. Okay, that's pretty simple. Let's see. Next problem. Okay, 2 more problems to go. 119 and 120. And I'm going to kind of race through those problems because this video is starting to get a little bit longer than I would like it to be. So, these are the directional derivative problems. They're fun, they're easy. You can definitely expect them on your quizzes and tests for chapter 12. Consider the function f of xyz is equal to 1 plus 4xyz. The point p negative 1, 1, negative 1, and the unit vector, okay, negative 1 over root 3, 1 over root 3, negative 1 over root 3. Compute the gradient of f and evaluate it at p. Okay, so here we go. So far, so good. Okay, here I'm going to pause just a moment so you can see how I generated this graph. Okay. What is the gradient at the point? Okay, so for this problem, I'm going to do some of the work myself. F, the partial derivative of f with respect to x is equal to, what do you think that is? Well, the partial derivative of 1 with respect to anything is 0. So with respect to x, it's going to be 4 times y times z. I could use Mathematica, but let's do this one ourselves because it's really not that difficult. And with respect to y, it's going to be 4xz. And with respect to z, it's going to be 4xy. What is the gradient? Clear gradient vector. So gradient vector is going to be fx negative 1, 1, 1, negative 1, fy negative 1, 1, negative 1, and fz negative 1, 1, negative 1. So that's going to be negative 4, 4, negative 4. Okay. What is the unit vector? Okay, 1 second. Let me move this over a little bit. What is the unit vector in the direction of maximum increase? Well, that's simply going to be the gradient vector, but we have to normalize it. So that's going to be the gradient vector divided by the norm of the gradient vector. And will they accept radicals in the denominator? Yeah. Let me make sure of something. So negative 1 divided by the square root of 3. Actually, let me move this over a little bit. So negative 1 divided by the square root of 3 1 divided by the square root of 3, and then negative 1 divided by the square root of 3. And that should be correct. Okay. What is the rate of change? What is the rate of change in the direction of maximum increase? So for that one, we're simply going to take the dot product of these two vectors. Okay, dot product, gradient vector, gradient vector normalized, so in the direction of maximum increase. Okay, and actually the vector they're giving us, the vector that they're giving us, this vector right here, it's in the same direction as the gradient. So that's simply going to be 4 times the square root of 3. And that should be correct. What is the directional derivative in the direction of the given vector? And actually, this is easy because they actually gave it to us. Now, I believe, okay, their notation is different from Mathematica's notation. So let me, well, I guess they're going to use, this is a little bit, okay. Hold on one second. The way Pearson does vectors is a little bit different. The way Pearson does vectors is different from the way Mathematica does vectors, so I hope I'm getting this right. So negative 1 over, hold on one second. Pearson can be a little bit annoying at times. So square root of 3, 1 over square root of 3, negative 1 over square root of 3. You know, something tells me Pearson will not accept this because of the way that I'm writing my answer. Hold on one second. Well, maybe it'll be okay, but this looks kind of weird. I think, yeah, the way Pearson writes vectors is different from the way you write vectors in Mathematica, so it's a little weird. Yeah, it's... Okay, I'm not... Here, hold on one second. The way... Okay, bear with me a moment. I'm trying to... Oh, maybe, hold on one second. How strange. Maybe... Okay, so they're not, hold on one moment. Final check. Oh, I misread the question. Sorry about that. Okay. I was obsessing over the wrong thing. Let me see here. What is the directional derivative in the direction of the given vector? So what they're looking for here, this was very simple. Yeah, I misread the question. I was obsessing over the wrong thing. So what is the directional derivative in the direction of the given vector? They're not looking for the direction of the vector or the vector itself. They're simply looking for the directional derivative, which is really the same answer we have here. So the answer, which is a scalar, is simply 4 times the square root of 3. Okay, so I was just, I misread the question. Sorry about that. But the answer, I mean, it's pretty simple. So what is the directional derivative in the direction of the given vector? It's simply going to be this value, this scalar right over here. It's 4 times the square root of 3. Okay. 120 is similar. Consider the following function f, point P, and unit vector u. Okay. So again, we're going to use Mathematica to help. So clear fx, fy, fz, and clear the gradient vector, because I'm going to have new definitions for those things. Okay. So the partial derivative of f with respect to x. Let's see. So with respect to x, we're simply going to have, this is my function right over here. xy plus yz plus xz plus 2. So the partial derivative of f with respect to x is simply going to be y plus z. Oop. With respect to y, that's going to be x plus z. And with respect to z, that's going to be x plus y. Okay. And then the gradient vector is simply going to be fx 8, negative 8, 7, fy 8, negative 8, negative 8, 7, and fz 8, negative 8, 7. Where, well, yeah, that should be fine. So we should have negative 1, 15, and 0. And let's see if that's correct. Wonder what happened over here. How strange. Maybe I figured out the wrong partial derivatives, but I thought they were correct. Let me see. Thought they were correct. F of x, y, z is equal to xy plus yz plus xz plus 2. Derivative of f of x and y and z with respect to x. Y plus z. The derivative of f of x and y and z with respect to y. X plus z. And the derivative of f x, y, and z with respect to z should be x plus y. Oh, again, okay, I think I'm going in a little bit too much of a hurry here. Hold on one second. So the gradient vector, compute the gradient of f and evaluate it at p. So y plus z, x plus z, x plus y, these values are correct for my partial derivatives. And we're looking at the point 8, negative 8, 7. Okay, so my partial derivatives are indeed correct, but what's really strange here is this should be the correct gradient vector. How strange. Very, very strange here. Okay, hold on one second. We're gonna cheat a little bit. Let me use Mathematica to help me. But I have a feeling the answer is going to be exactly the same. So x is replaced with 8. Y is replaced with -8. Z is replaced with 7. Yeah, and I am getting the exact same answer. Compute the gradient. Oh, I see. No, wait a minute. I don't see. Hold on. Compute the gradient of f and evaluate it at p. This should be... That's very strange. That should be the correct answer. I'm not quite sure what they are looking for. Very strange. Why are they hassling me over this? Oh, I see. Because they... Okay. They don't... So Pearson, for this problem, okay. They want the partial derivatives, but they don't actually want them evaluated at the point x is equal to 8, y is equal to -8, z is equal to 7. So they want the gradient in symbolic terms. They want the partial derivatives to be functions of x and y and z. So, okay. So then here they want the point -1, 15. I'm sorry, they want the vector -1, 15, 0. Okay, so that's a little confusing. So here, right over here, they want the symbolic partial derivatives in terms of x, any y, any z. And then here they're looking for, the gradient vector evaluated at the specific point, x is equal to 8, y is equal to -8, z is equal to 7. Okay. So the unit vector in the direction of maximum increase of f at p is... Okay, so just like for the last problem, we have to take... so the gradient vector is this value right over here, and we have to normalize it. Gradient vector, normalize it, so that's going to be the square root. Oh, sorry, hold on one moment. So that's going to be the gradient vector divided by the norm of the gradient vector. Okay. So that's going to be -1 divided by the square root. Hold on one second. Let me collapse this a little bit. -1 divided by the square root of 226. (15) divided by the square root of 226. And 0. Okay, the rate of change of the function in the direction of maximum increase at p is... So for this, we simply do the dot product of the gradient vector and the gradient vector after it's been normalized Okay, the rate of change of the function in the direction of maximum increase at p is the square root of 226. And that should be correct. Okay, the directional derivative at p in the direction of the given vector, it's simply going to be the square root of 226. Wait a minute. The directional derivative at p in the direction of the given vector. Oh, because the given vector, they're giving us some of these questions. They're not hard, but you really have to read them very slowly and carefully. The given vector that they're providing is this vector right over here. So hold on one second. So the given vector that they are providing, direction vector is equal to 0, 1 over the square root of 2, 1 over the square root of 2. Is this a unit vector? Yes, it is a unit vector because the magnitude is 1. So if we take the dot product of the gradient vector and the given direction vector, we're going to have 15, hold on one second, 15 square root of 2 divided by 2, which is the same as 15 divided by the square root of 2. And that should be correct. Okay, so with some of these problems, guys, you really have to read them carefully, and you have to ask, are they looking for, like here, my big mistake was they're looking for the general gradient vector, and my mistake was evaluating the gradient vector prematurely at a specific point. So for example, here, y is -8, z is 7, -8 plus 7 is -8 plus 7 is -1, and this is correct, but this is not what they're looking for. They're looking for y plus z, any y plus any z, and I was a little too specific. I was giving them, y is -8 plus z is 7, so y plus z evaluates to -1. So that's y plus z evaluated at this specific point, but that's not really what they were asking for. So, with some of these problems, you have to be a little, careful. You have to read them slowly and carefully. And, like I said, you do have 10 attempts on each problem. If you don't get it exactly right the first time, do it again for full credits. Okay, I think that's it. This video has gotten definitely long enough, and hope to see you in the next video. Take care and have a great day. Bye-bye.